take about 45 to 50 minutes. And I'll start with an introduction about AI, and then we will come down to a little bit to the technical side, and I'll take you through a small process of like a day in the life of a data scientist kind of a thing. How we apply, let's say, neural networks to solve a specific problem. Okay, so that's how we will start. Yeah.
It all begins from a single origin, a unique point in space and time. This is the spark of innovation that fuels your most amazing breakthroughs. It's a passion for discovery that unveiled the genesis of all that exists in the universe. Today, the power of AI helps computers achieve superhuman capabilities in image recognition and lets scientists save our most precious resources by analyzing in 1 month what used to take 10 years.
是谁发明了机械计算机？
Everyday devices translate even the most complex languages from voice into text and images into words.
Xavier is now present.
Helping the visually impaired recognize an old friend, or letting a blind woman read to her child for the first time. Autonomous vehicles give us the freedom to reimagine our city streets and travel where there are no streets at all to help the lost find their way home. We see robots teach themselves to perform simple tasks. We even watch in awe as they take their first steps. And today, a 2,500-year-old game meets its match as a computer competes with one of the greatest human champions of all time and wins. This is the collective imagination, fueled by forward-looking technologies and the beginning of your most amazing discoveries yet to come.
On March 15th, 2016, about a year back, something very amazing happened. How many of you are familiar with this? AlphaGo, right? Yeah, some of you. Yeah, so just like IBM Watson, which happened I think in 2011, yeah, right? So that was definitely a feat where a machine defeated a human champion or human champions. Similarly, this is another machine that defeated the human champion of a game called Go. Okay, now this is even more phenomenal. The reason being that this is one step closer to what is known as general AI. I'll talk about the different types of AI. Watson is what is known as an expert system, right? That is like a mid-level artificial intelligence. What we are aiming at is the next level, which is general AI. Now, what is the big deal about defeating somebody? Somebody in this game? Anybody knows what this is? Are these multiple numbers? No, it's just one single number. This is the number of possibilities in this game called Go. This is a 2,500-year-old game, Chinese game, and it is unlike chess, which has fixed rules. This game is actually very flexible, and it goes more on intuition. And this number is apparently equal or larger than the total number of atoms in this universe, I guess. Right? So you can imagine. So that is the big deal. And AI was used. The system is known as AlphaGo actually. Yeah, the application of it, or the system is known as AlphaGo, and that system was developed by DeepMind, which was acquired by Google, by the way. Okay, and before we come to this slide, now to develop Watson, it almost took, by the way, I'm an ex-IBMer, so I take the privilege of talking about Watson as well. So it took almost 10 years, I would say, right? A lot of work went on in the background, and to reach to that level, it took almost 10 years. But for DeepMind guys to come up with an application like this, can you guess how much time it took? It only took about 3 years, right? So that is the rate at which these systems are increasing, because of the computation power and so on and so forth. Now, AI is actually already here in some form or the other, right? We have talked about autonomous vehicles. Watson, actually, at time I was played another video of Watson. It's a very nice one. Though Mahesh has shown the technical side of it, this was really how the game was played. That would have been nice. And Siri, I think some of you already have iPhones and you must be using Siri, right? So it's already there to some extent, but you will skip this slide because we don't have to. Yeah, but what we are trying to, so again, as I said, the systems that we have now are a little lower level AI. What we are achieving, we're trying to achieve is general AI. And what are the possibilities of AI applications? I think that already some of the earlier speakers have talked about there are immense possibilities that what we can do with AI. They are used pretty much in every industry, not just, let's say, in army and things like that, not talk about that, but in pretty much every industry, every sphere of life, AI is going to be used. We already talked about healthcare. Yeah, Google is still working on this, how to detect and prevent blindness. And then there are already, like for example, with Watson, we have seen how to detect cancer and prevent cancer. By the way, Watson detects cancer, lung cancer, to the extent of 90% accuracy, right, with the new system that we have. Whereas on an average, I think doctors' accuracy rate is about 55 to 60%. Right? So that is in the lung cancer, very specialized in lung cancer. So what is AI? AI, by the way, while we are hearing this buzzword over the last year or two, and especially after this AlphaGo event, I think it has even more become a buzzword. But it has been there for quite some time. This word was coined way back in 1956, and John McCarthy is considered the father of AI. At that time, there was a conference, and they wanted to, work in this space. But unfortunately, after some time, they had to, cut short that because there were not enough powerful computers and so on and so forth. So that's where there was a period which we call it as the winter of AI. And then subsequently, from late 1990s, as the computation power increased, the focus on AI came back. Okay? So AI is classified into 3 types. One is the artificial narrow intelligence. That is what currently we are at pretty much. They are also known as the expert systems, which is the Watson and Siri and so on, which are AI systems which are very specific to do one kind of an act. Okay? What we are aiming at is artificial general intelligence. This is where an AI system can do multiple things. What we mean by that, for example, way back, I think, I don't know which year, but we already had a system which could defeat human beings, and Gary Kasparov was defeated, right, in chess, Deep Blue, right? Now, the problem with that was that it could only play chess, right? Now, if you wanted to train it to do something else, you need to wipe that whole thing, and then maybe you need to train it to do tic-tac-toe, for example, right? Now, a system like AlphaGo is currently capable of playing, let's say, multiple games, and they are still, of course, there is still work going on. So, as somebody pointed out, I think games is the best place to start building artificial intelligence, and that's the right place where these guys have started. So these Atari games they play, and towards the end I have a demo where they are training the systems, right? So now we have systems where these guys can play multiple Atari games. The same system can play multiple Atari games. This is no mean feat, right? Believe me. So that is where we are still not there, but we are trying to go there, right? So that is artificial general intelligence. But the highlight of this whole thing is artificial superintelligence, or what is known as, there is another term, singularity. Thank you. So singularity, right? So that is considered by some people as a very scary situation, because then the systems will be much more intelligent than us, and they may do anything to us. They may wipe out. There is a doomsday theory that they will wipe out.
Terminator movies.
Terminator movie style, exactly, right? So that is one school of thinking. On the other hand, there is another school, very more positive, saying that okay, artificial intelligence, these robots and all these guys will do the work. We will sit and enjoy life. We'll have more time to watch movies and things like that, right? So we don't know. That's still a long way off, because we are still not yet reached here. So this will take probably, I don't think I will see this, probably my children or grandchildren will see that, right? So, but that is I think that's what we are aiming at, right? So this is, Now, what is the important point to be noted here is that the time taken to achieve, let's say, artificial general intelligence will be like this one, right? The curve will be like this. Once we achieve that, it will be like a hockey stick. To achieve singularity will be much lesser. So let's say we take 10 years to achieve artificial general intelligence. Within 1 year, we may achieve singularity. So that's what this curve represents. Okay. So why now? I think there was another slide earlier also, and again, if we had time, I could have played a couple of videos. So there are a lot of things that are coming together for this whole thing, artificial intelligence, progress to happen. One, of course, is the power of computing, right? So we have the cloud, and then the Moore's law. I think some of you may be familiar. Computation power is increasing, doubling rather, and then GPUs and CPUs. I think there is a nice video I will play, but in the interest of time, I will not be able to do that. So it is not only at the software level, but at the hardware level, this whole thing is happening, right? The revolution is happening. So there are AI-specific chips that are coming up. Again, I hit some of the slides in the interest of time, but NVIDIA is leading that charge. NVIDIA is actually a hardware company, right? So it is at that level. From the bottom, it is coming up. And GPUs, anyone is familiar with what is GPU? Yes, graphic processor units. Now these are, earlier they were used in our video game consoles, right? They are very good at performing repetitive tasks very fast, right? Whereas CPU are more general purpose. Now, for doing machine learning, we need more the kind of GPU kind of chips, and therefore now they are becoming very popular, and that's one of the reasons adding to the progress with the AI. And of course, there are a lot of other things, like for example, huge investments. Elon Musk investing. What is this? The sun. What is his name? What bank? SoftBank. Right? SoftBank investing heavily into this. So there are a lot of stuff, everything coming together, and therefore there is a huge interest in this space. Now, so what is it under the hood? So under the hood, the technical side of it that drives AI is what is known as deep learning. And what is deep learning? It is a portion of machine learning. Right? We were talking about machine learning. Now it is a part of machine learning. One of the major differences is that deep learning uses several levels of or several layers. Right? That's why it is called deep neural network. So one of the key areas of deep learning is neural networks. And since there are several layers of in neural networks, it is known as deep learning. Right? The term deep learning comes in. Yeah, next. So machine learning, I think some of you must be already familiar. We can skip this slide, but the main thing is it consists of 2 or 3 components. Right? We talked about, I think earlier speakers also talked about. It is not like a regular program. Right? In a regular program, what you do is you give step by step every instruction, and the computer follows that, and then it performs the task. In machine learning, you don't do that. You give basic guidelines, and then the computer actually learns on its own. So there is a certain element of programming that is needed, like Python and R, or some of the Java also can be used. But a large part of it is algorithms and models, data models, plus large amount of data. Right? So these are like the 3 components for this. By and large, the machine learning is divided into supervised and unsupervised. but of course, there is another reinforcement learning recently is coming up, and I'll show you a demo on that as well. What is supervised learning? Supervised learning is where you tell the system, okay, let's say you want to categorize a basket of fruits, and you want to teach the system to categorize that into, let's say, bananas, oranges, and apples, right? So you provide an example of a basket of fruits saying, okay, this is an apple, this is an orange, this is a banana, right? That is called labeled data, right? And then when you show an apple, it will immediately classify, yes, this is an apple, right? So that is supervised learning. Unsupervised learning is more used when you want to do some exploratory activities. You also don't know how many categories of fruits are there, right? But you know that, for example, you have a bunch of, you have a data for a bunch of animals. So you know that these animals have, let's say, 4 legs, and the length of the legs is known, length of the tail is known. So these are all the features, but you don't know how many types of animals there are this data consists of, right? So you tell the system, okay, take this data and you cluster them based on these characteristics, and then the system will come up and say, hey, you know what, there are 4 types of animals here, looks like. But though the system may not know whether it's an elephant or a tiger, right? So that is unsupervised learning. Reinforcement learning is again very interesting. Here there is a system called an agent and an environment, right? And this is very good at when we are doing games, right? So here the system will have a certain set of tasks to perform. Maybe go to the right, go to the left, and then it has a goal, which is increase the score, for example, right? And it keeps performing this task, and whenever it, let's say, increases the score, it gets a reward, and whenever it, let's say, it loses a point or something like that, it gets penalized, right? So the system keeps learning, and at some point it will become much better than even a human player, right? So we will see an example of that. So what are some of the techniques or algorithms that are used? These are some of the, I think some of you are already familiar. Let's skip this in the interest of time. But yeah, so in the whole process we use some of the data mining processes, classification, regression. I think some of these terms we have already heard. Clustering, I just talked about. Anomaly detection. Anomaly detection is again when we do, for example, clustering, right? So you will have a set of data which is very similar. Clustering is nothing but you cluster data points which are very similar to each other. But within that, there may be an anomalous point, right? So something that stands out. So all the data points are in one place, but one data point is somewhere here. So that is an anomaly, right? So that kind of anomaly detection is used, for example, in fraud detection or when penetration into the network, hacking, and so on and so forth. The anomaly detection technique is used. So this is the process of how you train a system, right? So let's say in a supervised learning process, this is how it goes through. So you have the label data, as I said, which already has the information, and then you do a little bit of the feature extraction. This is nothing but you say, okay, length of the tail, the length of the leg, height, weight, these are all the features, right? And then you decide on a model or an algorithm, and you say, okay, I'm going to use this particular model, and then you train the system, okay, and the sample data, you basically split it up, saying training data and test data. With the training data, which typically is about 80%, you train it, and then you test with the known data, and then identify whether it is doing well or not. And if you are happy, then you put it into production, otherwise you continue to tweak it, okay. So that is the overall how the process works. We'll skip this slide. So deep learning is, as I said, is a part of it. So deep learning consists of neural networks, and the whole idea of neural networks is to simulate the human brain, right? So learning process is nothing but you're telling a machine to learn something, just like you tell a small child to learn something, right? So you say, okay, look, this is if the fruit looks round and red in color, it is an apple, right? Something like that. So the number of, so basically neurons, this is basically a slide showing how many neurons are there in various types of living beings. So human beings, for example, have maximum about billions of, I think, neurons. This is how a single kind of a neuron looks like, artificial neuron, by the way, okay? So there is, what it does is it takes inputs from various sources or whatever, and then it takes, it kind of does a calculation and it gives an output. The calculation is basically, it multiplies with some weights and then it adds something known as a bias. So it is, if x is x1, x2, x3 are the inputs, then it will add weights like w1, w2, w3. So the output will be w1, w1x, x1, w2, x2, w3, x3 plus a bias, and that will be your output. Now this output can be like a 0 or 1, which, and in artificial neuron, we call this as an activation function. So there are different types of activation functions we use. Sigmoid is kind of the more very common one, but nowadays the new one, which is ReLU, right, which is being used. In case of sigmoid, it goes from 0 to 1. The output goes from 0 to 1, and again, so it classifies whether it is a 0 or a 1. In case of ReLU, also it is 0 or 1, but it is more linear. Whereas in case of a tan H, it is minus 1 to 1. Okay, and there are different advantages, disadvantages, and there are different situations where we use different activation functions. So this is a very basic representation of a neural network. It's pretty much like every neural network will have an output layer and an input layer, and then for some reason it is called hidden layer, but that is where all the actual calculations and computations happen. And there will be several hidden layers. So next slide, please. So this is why it is something known as deep neural network, right? Because there are several layers, and typically to solve a complicated problem, you will need several layers, and that's the reason it is known as deep neural network. So you still have the input layer, output layer, and then several hidden layers, which are basically where a lot of computation happens. How much time do I have? The neural networks are kind of classified into two types. Feed-forward neural network, where the information goes only in one direction, right? The input comes, get how computation happens, and then output comes out. And next slide. And there is one more known as recurrent neural network. Here, in some cases, what happens is you need to provide some feedback to the system, how accurate it is, and sometimes it needs some memory also to retain some of the information. So that is where we use like LSTM and so on. So that's why we use recurrent neural networks, where there is a feedback provided. So some information goes in the backward direction. All right. So what we'll do is, if we have time, I need to do a time check. Can I go? Yeah. So a small process of how a data scientist goes through solving the small problem, right? So this is like a hello world for neural networks. So when we learn Java program, what we do, we write one line saying hello world, right? So this is like a hello world for neural network. What I'm going to do is, I have a problem where I want to detect handwritten numbers. Okay? And by the way, this is a classical one, I did not invent it, so look at that. So how do I go about solving this problem? So, right? So let me just show you one quick demo. Demo. So again, this is available. You can see that link. Anybody can use it. So what is happening is, it is recognizing. So this is the input, okay, and these are handwritten characters, right? You know, handwritten characters can be quite complicated. Each one has a different type, and it is able to recognize it. See here, this is the input and this is the output. It is able to recognize the numbers which are handwritten. Now, not only that, this system is so stable. Even if there is some noise, disturbance, if the numbers are dancing, even then it will detect. Just take it. Okay. So in that screen, if only 84 appears, it is saying 84. If it is 384, it is 384. Not only that, if there is any noise, right? So let's say noise B and 6. Okay, it still recognizes. See, there are some lines and so on, but so it's such a stable system, right? Just to give you a quick idea. Now going back to our presentation. Alright, so how do we solve this problem? We can, obviously we start with a very simple neural network. Next slide please. What we'll do is, okay, we'll skip this, we know how to do this. We will take a very simple, kind of one layer neural network, and softmax again is one of the, let's say, activation functions we'll be using. The way this will work is, there is an input layer and there is an output layer. Input layer takes input from the pixels. Output layer tells whether, and there are 10 neurons in the output layer, right? Depending on whether it detects 0, 1, 2, 9, one of them will be activated. So one of them will give us a 1, right? So it's very simple. And only thing is that, keep this in mind, I'll come back to this later. Only thing is that the pixels, we are going to flatten them. In the sense that I take maybe one end and then take all the pixels, straighten it out, and that will go as the input. Okay? So what happens in this case?
So when you flatten out, you're saying you take a squarish thing. You take the top layer, the next layer, like that.
No. It's one line. So I take
all the rows are put the end to end.
Yeah. So I start from maybe left hand corner and I say, okay, I stretch the whole thing. So it is like a one line kind of a thing. I lose the shape. I'll come back to that actually. Okay. So I wanted to keep that as a suspense, but he asked the questions. No issues. So okay, so we start with that because I want to keep it simple. So I'm starting again. As I said, I'm putting the hat of a data scientist. So this is how it works. So output of the neuron, single neuron will be something like this, and overall output will be like a matrix. Can we go to the next slide, please? So this is like, since we have 10 neurons, the output will look somewhat like this. Next slide. One more. So this is again output. Alright. So if I just use this very simple neural network, I still get pretty good result, right? For my little bit of effort, I have achieved 92% accuracy. Okay. So how do I do this? Obviously, I need to have some labeled data, as I said, right? So I have about 1,000 data or 1,000 points I have taken as of labeled data, and I have split it into, let's say, 80-20, 80 for my learning or training, and 20 for my test. That's how typically we do in regular machine learning. Also, we do that. Okay. Now, there are a few things we need to learn about here. So when I am trying to test the stability of my system or the accuracy of my system, there are two things I will have to check. One is obviously the accuracy. How many of them are correctly detected or predicted? We say prediction, but it is not prediction in future. But what we are saying is the correct value, predicting the correct value, right? So that is one for both my training data as well as my test data. And the other is, this is a new term for you, cross entropy loss. Cross entropy loss in simple terms is nothing but the difference between the actual data and the predicted data, basically the error, right? So that is also something we need to track. So in this case, I'm getting 92%. Typically, we may be happy, but then this is still not production grade. Why? Let's say I want to use this for, our postal department wants to use this, right, to send out our letters. Now imagine how many digits are there in the postal code? 6, right? Now every digit, if there is a 8% error, with the 6 digits, how much do we have? 6 into 8? 48. Almost half of the letters will go to the wrong place, right? So it is not enough.
So what is the 0.08 power 6?
0.8 power 6?
Yes.
Okay, yeah. So still the error is still
it is considerable, but
considerable, right? Yeah. So that's the point. I'm just trying to simplify it. Okay. So we cannot be happy with this. That's the point, right? I cannot be happy with this. While 92% in absolute terms looks okay, but I cannot. So what do I do next as a data scientist? Okay. Before that, I want to explain a few terms. As I said, right, as we go along, we will learn as well. So this is how my code, Python code will look. I just took 2 lines of code out of my whole thing. There are a few things here which are like, the cross entropy, you remember I mentioned. So what is my cross entropy? That is what I'm using in my optimizer to minimize. Basically, I need to minimize that error, right? So this is the second line of code that I right? And then I need to use an optimizer. Optimizer is basically something that will help in reducing. While doing the training, that is what will help in reducing the error. Okay? And there are several algorithms for this. In this case, I am using gradient descent. So what is gradient descent? As the name suggests, it is like we are at the top of a hill when we are starting off, and then we slowly have to come down so that the error becomes zero, right? When we start training, obviously the system will give a lot of errors. By the way, when we start training, the weights and biases will be random. Some random numbers will be assigned and it will start, and then as we progress, they will adjust in such a way that the error becomes zero, right? So it is somewhat like a valley, right? So there are two hills and a valley. So you need to then tell the system that, you take small steps. So if you are at the top here and if you want to come down, what do? You try to find out the path which is easiest to come down, and step by step you come down, right? Now, there is a point there, learning rate, right? That learning rate is key here. That tells how small the steps should be, right? Now again, here there is a challenge. The best way is to keep as small as possible, but then it will take forever to come down, right? So we need to have a compromise, and we give a certain value based on your computation and how much time you have and so on and so forth. You have to give a certain value. So in this case, I have given 0.00 learn rate. Okay. If you give too high a value, what will happen is, instead of coming here, it will go to the other side of the value, right? So it will oscillate, which is again not a very good thing. Okay. So these are some of the terms we learned. Okay. Next slide. All right. So we will now apply that here. And can we go to the next slide? So what I'm going to do now is, I see that 92% is not enough for me, so I'll go deep, right? I'm doing deep learning. So I will say I will use 5 layers, okay? And I start off with my after the input layer, the first layer at 200 and 100 and 60 and 30, and then of course last layer will still be that 10 because I need to get that output, right? This is known as a fully connected layers. Now, there is a difference between fully connected and later I'll touch upon convolutional neural networks. Fully connected means every neuron in each layer is connected to, or the output is connected to every other. Okay, so that is a fully connected.
So you picked up 5 as a trial number of layers as a 5 years?
Yes, yeah, exactly. Yeah. I have to start somewhere. I said, okay, I'll take 5 layers. I can do more also, but again, it needs more time. Training also will take longer and so on. So I said, okay, let me start. Again, as I said, that's how a data scientist has to work. A lot of trial and error goes on like that. Okay? So, in addition to that, while here I use softmax, for my other regular ones, I am using sigmoid, which is a very common one. Okay? So now, if I try to run this, what happens? Yeah. So what I do is, now that I have kind of changed my architecture, I just test it with a few small set of samples, which is about 300, and I find that it's not working, right? I would have assumed that my accuracy would have increased and so on. So I will do a little bit more tweaking. Instead of sigmoid, I will change to ReLU. Okay? Now there is a lot of theory behind why, but the basic point is that ReLU gives better results. So let's accept that and we use ReLU. And again, I try with my this 300. I see a big improvement in the whole thing, right? So the learning, the rate has increased very sharp, very quickly it has learned. So now I go with my 10,000. Yeah, next slide. Okay, it looks much better, right? And what's the good thing about this is that for the first time, my training accuracy has touched 100%. So out of that 80% data set that I'm using for training, it has perfectly recognized all of that, 100%, right? Of course, that doesn't mean it will always do it. That may not be a very good thing as well. You will see that a little later. My test accuracy, of course, is still around, I think it is 98%, which is reasonably good. Now, but still there is a problem here. I'm not happy. Why? It is noisy, right? So you see here, the spikes. So whenever those spikes are there, that means still not stable. So I would like a smooth curve. Okay. So what can we do? Next slide. You remember that learning rate I mentioned, right? So that is where the key is in order to reduce the noise. Now that I have the flexibility to change it in such a way that initially I will keep it a little higher because 003 as such is not very high, but still it's relatively high. because I want to, climb down a little faster, but as I reach the bottom, I want to take smaller steps, right? So I use a technique called, can you go to the next slide? Learning rate decay. Okay, so what I have a possibility to say that you start off with 0.003, but as you reach the bottom, you change it to or reduce it to 0.001, right? So that helps me in as I reach the lower towards the bottom, it will the steps will reduce and my the curve will be much smoother. Okay, so that is another technique I apply. So now accuracy is good, noise is good, but still there is a problem. What is the problem? Do you see a problem here? Huh? Yes, exactly. It is increasing, right? This should come down. For training, it is fine, but for test, it is increasing, right? So this is where a problem called overfitting, right? You remember, we were very happy that my training data reached 100%. That is the problem, right? Because you are teaching in the system so well that it recognizes those set of data very well, but some new data that comes, it's kind of failing, okay? And this is a common problem. So what we do here, we can skip that. So the term there is overfitting, okay? Again, this is a common machine learning problem. So there is something called regularization that is used for overcoming overfitting, right? So what we do in this case in neural network is something known as dropout. So basically for the learning phase, we just shoot out some of the neurons, all right? So we say that there is again, if you use TensorFlow, the API provides it, there is a parameter called pkeep. We say pkeep 0.75 means 25% of the neurons are shot out. Randomly, by the way, okay? They will not change. But then that is only for training. For test, you still have to keep all of them. Okay? Thereby what you are doing is, you are not overfitting or overteaching the system. So it is okay during learning process if it doesn't reach 100%. But at least during the test and during the actual prediction, it will give us a better accuracy. So now let us see what happens there. So we got, okay, this is initially how we started, right? With the sigmoid, with the learning rate, 0.003. So I'm just showing you step by step how it was improving. Yes, once more. Okay, this is where we reached overfitting. Now to solve this overfitting, we did dropout, and this is where we are. Okay, so this is kind of without using convolutional neural network with the fully connected system. This is kind of the best we can achieve, which is 98.2%. Okay, if you want to go beyond this, it is pretty much impossible with the current architecture. The reason being, right, the suspense was broken at the beginning. The reason being, we are losing out on the shape, right? So we said we will take this whole thing and spread it out, right? We will straighten out. Next slide, please. At the beginning, yeah, right? So we said we stretched out the entire thing, so the shape information was lost. But in order to do with a fully connected system, that was the only way we could do. So now, in order to retain the shape as well and to use the pixels in the same way, we use what is known as convolutional neural network. It's a little difficult to explain, but I will take a shot at it. So here what we do is, instead of connecting all the inputs to all the neurons, okay, we do like a sampling. Okay, so we take maybe a 4x4 of the patch, and we keep moving one by one. Okay, before that, okay, this is the input. This is the first hidden layer, and then there is one more. There's what is known as the pooling layer in between, and then you will have towards that there will be a fully connected. I think in the next slide you will see that. Okay. Now, within that, these pictures are trying to explain what is going on. So in these first two, what we are doing is we are taking a patch and we are passing it to the next layer, first hidden layer. Okay, and then we move that patch to the right. That is what is termed here by 1 pixel. Okay, and then we are passing it to the second neuron in that level, right? And so on. So we are basically doing some kind of a sampling.
And if IFL is still stretched out, right?
No. No, this input is you are taking the complete image as it is, okay, and you're sampling. So thereby the positional reference is retained, integrity is retained. Here you are not stretching out the pixels. Here you are taking the image as it is, and then you are sampling. So this will actually, what it does is it does like the feature extraction. So there will be multiple layers. Within each layer there will be again multiple layers, okay. And each of them will identify one characteristic. Maybe one is a horizontal line, one is a vertical line, one is a curve, and so on and so forth. So then it will be able to, identify the images more accurately. Can you go to the next slide? So this is how a traditional architecture looks like, which is basically a convolutional layer alternating, right? Convolutional layer and pooling layer. It alternates, and there can be multiple. For simplicity, I just put one, but there can be multiple such blocks, right? There may be 3 or 4 alternating convolutional and pooling layers, and towards the end, obviously, it will go back to a fully connected layer, and then to the softmax, which is the output layer. Okay, but in later part, nowadays, what we are doing is we are kind of avoiding the pooling layer with the help of what is known as a stride. So stride is basically, instead of going 1 pixel by 1 pixel, right, we take 2 or 3 strides, right? So which means we skip 2 pixels or 3 pixels, thereby we are overcoming the pooling part of it as well. Okay. So again, as I said, probably it's too short a time to explain everything, but let's accept that this works. Okay. Now if I apply convolutional neural network, I definitely see a big jump. So I have reached 99.3%. Right? So here, because we also have the shape and the positional integrity, we can achieve much higher accuracy. So that's, I think, a quick overview of how we can go through this process. Next slide. So CNN is used very commonly nowadays for image recognition and so on and so forth. And in fact, each of these layers, as I mentioned, in a regular, let's say, image recognition, they do what is known as feature extraction. We typically otherwise do manually the feature extraction, right? So these layers actually do automatically the feature extraction. All right. So while we are at that, there's one topic or one point I wanted to talk about. Next slide. Yeah. So reinforcement learning, I was talking about, right? So what is reinforcement learning? This is one slide on it. What it does is, this is how it looks. So there is an environment and there is an agent. Today it is used, for example, the AlphaGo game that we talked about, that was done by reinforcement learning. Okay. So there is something known as agent, there is something known as the environment, where basically the game is the environment and the agent is basically your program, and it takes actions and the state is managed. Okay, the actions, there may be 1 or 2, move to the right, move to the left. It could be simple actions, and then there is a reward and there is a goal. Right, the goal is to maximize the points, and that is the and if it is moving towards that, then it will be rewarded. Otherwise, there will be a small punishment. Right, so this is how it looks. Now, I would like to show this a small video how it works, and then we will end. There is no audio here, so I'll just talk through this. So there is, some of you may be familiar, these Atari games are, the pixel kind of games. Sometime back we used to play like Pac-Man and so on, right? So some of those games, they used deep learning to train or build a system for playing this game, right? So this is how it looks when it starts off, right? So it's pathetic, it is losing out. Obviously, it's still training, right? Okay. So that's the score, and that is the number of lives. Okay. Now, after 2 hours of training, right? Just with 2 hours of training, it's now playing like a pro. It's not even allowing that thing to fall, right? Okay. So the score is consistently increasing, the lives are intact. Okay. Alright, now what happens after 4 hours of training? See, this is really fun. It's become much more expert. And it figured a technique which no human being could have thought of, right? So that is the power of deep learning. Okay? So I think with that, I would like to end my session.